And most of it y'all had, and some of y'all had in motor control. So everybody in here has had motor control. So that part of the lecture should be just simply a review. So mechatronics. What is mechatronics? Huh? Well, that's what it was originally set up to be. When they first came up with the buzzword, they said, okay, mechatronics is a combination of mechanics and electronics. But then they finally realized that as automation kept going, they realized there was more to an automated system than mechatronics. So this is basically what mechatronics is right here now. So this is mechatronics. So mechatronics consists of a multiple trade or craft. Um, so this is off the website, by the way. You can search for this. So it deals with control systems, control electronic systems, electronic systems, electromechanical, mechanical systems. Has a little bit to do with CAD, computer aided design, and of course computers and digital control systems. So you can see mechatronics now is a lot more than just what electronics and mechanics. So this is where we're sitting right now, and of course this should come into play. So mechatronics has all kind of stuff involved with it. And the Siemens certification is a mechatronics certification. It's Siemens Mechatronics System Certification Program, and that's what they call it. So normally, what we try to do, and what Siemens certification does, is try to teach what they call the system approach. So originally, what we used to do, and we did this for years and years and years, is we taught all the components first, and then we taught the system. Mechatronics, what do we start with? We start with the system, and then we move to the components. So last class, we only had one person show up for the first class. What did we do a lot of the class, Kareem? We went back there and what? We went over a lot of what's going on with the system and see how the system works. And we'll look at that a little bit more tonight. So it's very, very important to look at a system. So this is the system approach. So we start off with the what? We start off with the system. Then we'll move to the modules. Then we'll move to the applications of the system, the characteristics and design function, physical principles and characteristics. Then we'll start working with troubleshooting. And then when you get through that, we'll move to y'all move to another module. So we have two manufacturing lines. The Festo is not quite ready for the way the course runs, and since this is a pretty small class, we'll be just strictly on the Amtro line this semester. So electrical, fluid power, mechanics, and control. So this is basically what we're going to deal with. The PLCs, we're not going to deal with from a programming point of view. We're going to deal with it in from a port point of view, from not trying to program it, just trying to figure out basically why it's in the system and what problems it can go. So we're going to deal with safety, which is what we dealt with last class, and the systems. We started with that. We'll look at those tonight since some of y'all missed, and that's very important. And now what we're fixing to do is we're fixing to look at basically a review of electrical, fluid power, mechanics, and PLC. And then we'll look at some of the documentation that goes along with understanding or troubleshooting these things. So this is where we're at right here. So this is the next PowerPoint, and this is a topic review. And we'll start off with electrical. Of course, y'all understand we have two types of power sources, right? Electrical power sources. Now, when we talk about power sources are devices that create work or cause things to move, right? So primarily in mechatronics, we have three different power sources. We have electrical power, and then we have pneumatic power, and then we have hydraulic power. And of course, we don't teach hydraulic power over here. In fact, we teach hydraulic power in fluid. If you take the fluid power course, the hydraulics and pneumatics course, but we don't actually do labs on fluid power anymore because fluid power is a lot more dangerous than pneumatics. So you get over there in pneumatics and you don't hook up a pipe right and it breaks loose. It's going to jump around and it might bop you a little bit. You get on a hydraulics and you don't hook up a pipe right and you're dealing with 3,000 pounds PSI pressure and a pipe comes loose, you got big problems. Plus, hydraulic fluid is very slippery. So now not only do you have, hydraulic fluid flat, then you can't even stand up anymore because it's oil, right? You understand? So we don't do hydraulics anymore. We don't let you do labs, but the technology is so similar that when you learn one, it's very easy to pick up another. It's just like in PLCs. If you learn one PLC, it makes it real easy to do what? Pick up other PLCs. Like when you want to learn one program, when you learn how to program, once you understand the logic, it makes it real easy to pick up other ones. And why I said that, we got our Arduinos in yesterday, so I've been playing around with it. So the two electrical power sources, we have DC and we have AC. Of course, in DC, we have voltage, we have current, we have opposition, which we call resistance, and then we have power. So power, we're going to be concerned with. AC, we have voltage and current, but in AC, we have three types of opposition. We have what we call, actually two. We have resistance, and then we have something called reactance. And we have two types of reactance. We have what we call inductive reactance and capacitive reactance, which we need to understand a little bit about when we get into motors, because this will explain how single-phase motors spin. And also understand some other stuff. Of course, conductors in electricity, we have copper, we have copper alloys, aluminum, we have stranded, solid, and we have fiber optics. Now, what's fiber? So all these at the top, this is sending electrical current. So we're transferring our power with volts and amps, right? You understand? In fiber optics, we're not transferring power, we're transferring information. So with copper, we can use copper or metals to transfer either information or power. You need to understand the difference between the two. So if you're thinking about your car radio powers off your electrical system. The signals to the radio comes in from the antenna. So I can't do anything with the signals unless I have a power source, right? You understand that? So, but if you look at the conductors in electrical, your information conductors are basically the same. They might be smaller as the conductors that we send power. Fiber optics, we don't send power. The only thing we do on fiber is send what? Send signals or send information. So the power would have to come to power your fiber optic system comes from electricity. So fiber is basically strictly. Anybody know what advantages fiber has over copper? Speed, but why? Well, speed, we don't have to worry about, we do have to worry about opposite. We call it attenuation. So it's almost impossible to get something that don't have loss over distance. And of course, we have two major categories of fiber. We have plastic and we have glass. Glass has a lot less attenuation, but it costs a lot more. So all our fiber over here on our line is plastic. Okay, but we transfer light. We don't have to worry about reactance. Changing signals have to worry about reactance. So there's a lot of things when you're sending communication cables that we have to take in consideration that we don't have to do in fiber. And then there's a lot of stuff in fiber that we have to take in consideration that we don't do in copper. And anytime I want to send information, one big advantage of fiber is that we don't have to worry about electrical noise. Not to worry about it at all. A lightning can strike right next to fiber, it means nothing. lightning strikes next to copper, you got big problems. So fiber is very immune to electromagnetic interference, totally immune to it. And the bandwidth, since it don't have to worry about reactance, the bandwidth for fiber, which means the amount of information we can send, is extremely high. So we can do it at extremely high speeds, but we still have problems. If you want to learn more about fiber, you need to take the cable splicing and installation course. Control devices, switches, contacts, and sensors, and then, of course, PLCs. I did something, and I should have done that and put that in this slide. Basically, when we deal with control systems, we're dealing with three main elements. And y'all in the sensors class, what does a basic control system consist of? Inputs. Well, in the center. Got to put the center in there. How's that, guys? I'm trying to get to my marker. So basically, a system or control system consists of inputs, and then we feed into some type of control logic. And then we're going to do what? Then we're going to have to develop outputs, and that's basically what a control system does. In motor controls, you learn relay logic. Over here, we're using what they call programmable logic controllers. But that's the logic, right? Y'all understand that? What's nice about PLCs is they're programmable. So all the control logic in there is written by a person. So it's real easy to modify. Plus, it takes up a lot less space than relays. That's one of the other big advantages. But they also have microcontrollers, which I'll show y'all some later on. But these are basically programmable, but they don't have the power that a PLC has. But still, they cost the one that Thomas plays around with called Arduino, and that sucker's only got $30, and it's a really powerful little microcontroller. So you'll see these used a lot because they're so cheap. They're programmable, a little harder to program, and they use a little higher level language, but they're so cheap. So you'll see these doing basic tasks. So they might, we might go out and get a display, and we hook it up so that we've got that HMI panel over there. Well, that HMI panel itself might be ran by by a microcontroller that feeds the PLC. So these are pretty neat. So different type of control logic. So basically, we're over here on the input section right now. So we're going to start dealing with, of course, signals, sensors, and that kind of stuff. Control devices, of course, these are considered to be input devices. These are considered to be sensors, even though a lot of people don't realize that, because what do they sense? Well, they sense you, right? Doing what? Mechanically reacting to something. So we have push buttons. We have push buttons, we have switches, basically pretty straightforward, right? Okay, you understand that. So we look over here on our manufacturing line, and we see all of them. You got push buttons and you got switches, and sooner or later in a control system, you're going to run into push buttons and systems. Automation's really neat, but somewhere, guys, a human is going to have to control some section of that, right? You understand? So somebody's got to have the ability to turn it off. I was talking about the U2. The U2 spy plane is really old, and they were talking about how much it played roles in some of the things they were doing over in Afghanistan and Iraq when the war was going on, even now. And they said the military was trying to replace it with drones. And it says they don't really think they're going to be able to do that because they're taking away the human aspect, right? You understand? Being able to make decisions about things. The U-2's a neat plane. I've been around a few of them. Watching them take off and land is something else. But that thing flies around 72,000 feet. And the SR-71, it flew up at 80,000 feet, and it flew over Mach 3. But it took about $1 million to fly that plane every time it took off. So the SR-71 has been decommissioned, and I think there's only one or two still flying. And but the U-2 is still out there. I think they still have 33 out there, I think. So sensors fall in two major categories. We have what we call digital analog. So everybody knows the difference between those. Yeah, but analog is a continuously varying signal, right? You understand? A digital is going to change. Our digital sensors change in steps. They're either on or off. Or they either give us a high, what we call a high, they give us a voltage, or they give us a ground. Okay. So all the digital sensors that we've got on our manufacturing line deals with this. Some of the ones we'll look at is limit switches. We'll look at proximity switches. So a proximity switch is a sensor that indicates when something is at a location. The first proximity switch that we ran into were limit switches. These are mechanical devices, and so they have their own name. Even though they're proximity switch, we don't use the name proximity switch. We use the name limit switch. So usually limit switch is in a category by itself. Normally, when we use the term proximity switch, we're talking about solid-state electronic switches, where a limit switch is a mechanical switch activated by something when it gets to a certain position. A proximity switch uses some other form to determine when it's at the same position. So now when we use the term proximity switch, we're usually talking about the electronic switches. Sort of. So our proximity switch, we have photoelectric, through the beam, optical interrupters, diffused, and retroreflective. We've also got inductive proximity. We'll look at those, capacitive, reed switches, Hall effect, and ultrasonic. So most of your proximity switches, that's another thing that I should also mention, these are what we call non-contact switches. So you'll know what that means. That means it does not have to make physical contact with what it's trying to determine is at a certain position. Okay. A limit switch has to make physical contact with what it's trying to determine is at a physical position. Okay. What advantage would you think the main advantage to a limit switch would be? Why are they still used all over the place? Yeah, they're real cheap. No calibration, no sensitivity. All that's determined is how you have to say. Very, very sturdy, lasts a long time. The only thing is they're electromechanical devices. And when I use two terms like that, it means two things could fail, right? They could fail what? They could fail electrically or they could fail mechanically. Just like your car. Your car is an electromechanical device. So how can it fail? It could fail mechanically or it could fail what? Electrically. And unfortunately, sooner or later, one of them's going to get you, isn't it? Yeah. Non-contact sensors flow. We'll look at pressure, flow. I don't know. What we might do in this class is just limit the sensors to the sensors that we're going to run into on the line. So all y'all got to take the sensors class anyway. So most of these over here we will get into in that class. So we'll probably, in this class, what we'll probably do is just limit it to the sensors that we'll run into on our line. And then look at the diagrams and look at the symbols. So analog, what analog? Temperature analog, light would be analog, right? Pressure would be analog. So we got a lot of things that are analog. Digital is going to look to see when something gets to a certain, so if it's a digital pressure switch, it's going to look to see when something gets to a certain pressure. Right? You understand that? A light digital switch is it's not looking at the intensity of the light, it's looking when the light gets to a certain what? Potential, right? You understand that? Which they can use it to, we'll look at some of the things they do on the Festo line, which is pretty neat what they can do with some of their light sensors. Where digital is going to give us a discrete output. I mean, it's either going to be there or not there, right? You understand? Huh? These are some of our analog sensors. The only analog sensor we have on our line that's usable is what we call a potentiometer. And what we do is we attach the potentiometer to whatever's in motion, and then when it moves, it changes the resistance to this point right here. Now, if we put a voltage across A and C, then what happens, the voltage off of B will vary depending on the position. And that's an analog output, right? You understand that? So we use one of our lines, the Festo line uses a potentiometer to measure the height of the cylinders. So if the cylinder's not the right height, it's going to reject it because it goes to a device called a analog to digital converter. We'll look at it in a minute. So ADCs. This is we have an optical encoder on the on the Amatro line. It's measuring the distance that the belt travels, so it knows how to do certain things. So encoder, we won't look at that. What the line uses, it uses what they call an incremental encoder, which is this guy right here. So an incremental encoder has got a bunch of stripes, and it shoots a light beam through that, and every time a black line comes on, it breaks the light beam. Does that make sense? And then the two sensors are actually offset, so when one is seen, the other one is blocked. You know, see that? And they're offset for like 45 degrees. Not 45 degrees, looks like maybe 10 degrees. What happens is we get two digital waveforms off these things. And what these waveforms do, so notice A occurs before, A occurs before B. If it rotated in the other direction, then what? B would occur before A. So what we can do with these is not only can we tell position, but we can tell what? We can tell speed. So the robots use an incremental encoder for two things. Not only does it give the position of the robot, but it also tells it which direction the robot is moving. And it also tells the controller what speed the robot's moving at. Because the faster the pulses, the faster the speed, right? So what's nice about an incremental encoder is it can serve two functions. Not only can it tell us a position, but it can also indicate a speed. So let's look at proximity switches. These are limit switches. So we have two types of limit switches. We have what we call a pilot duty. These guys are designed to run loads. These guys could handle a pretty good voltage and handle a pretty good current on their contacts. So if you got into motor controls or stuff like that, then you would run into what we call pilot duty limit switches. In my show and tell boxes in the other class, I'll try to go around and show you. I'll let y'all hold a limit switch. Then what we have on our lines is we don't have pilot duty. We have what they call electronic duty. Electronic duties usually are designed to be inputted into a control logic like a PLC. So these guys, PLCs don't require much power on the inputs to operate. Does that make sense? That means these limit switches can be really, really small. Well, fairly small. I mean, you can see them. They're not so small you can't see. These are called electronic duty. So what we'll see on our manufacturing lines is all the limit switches on the manufacturing lines are electronic duty limit switches. This guy, I think they're all referred to as micro limit switches. It's just what they changed is what we call, a lot of them have different, what we call operators. Operators are the device that causes the limit switch to operate. So notice some of them have rollers out there. Some of them just have little flappers. Some of them are what we call push limit switches. So instead of operating on an angle, you literally push, the operator pushes up into it. And these are basically almost the same categories that we have for your pilot duty or your high. But most of these are called micro limits, are called micro switches. That's what, if you looked them up on a parts list or going to a parts store, that's probably what you would call them. Yeah, so that's a good point. Any more points? Yeah, they're cute. Most of the ones on ours, I think, use these rollers, but we'll go over there and look and see. So there's several of them on there. Like I said, the biggest advantage of these things is basically their cost and their ease of installation. You don't have to worry about setting sensitivity. So most of your proximity sensors are actually analog sensors. The system element is analog, but we're bringing them into a PLC. We're bringing it into a digital input. So to go from analog to digital, we have a circuit we call analog to digital converters. And these are all what we call single-bit inverters, which means they only give us either ones or zeros. That's all they give, or highs and lows, a voltage or a ground. Well, what happens is inside the sensor itself, and most of your solid-state sensors have to be powered. So they'll have at least 3 wires, 2 for power, 1 for the signal. Does that make sense? Some of them have 4 wires. Well, the 4-wire sensors basically has a normally closed contact and a normally open contact in it. Your 3-wire sensors usually only have 1 contact, and it's usually a normally open contact. So that's the way you can, and the color code is pretty standard. We'll show you all that too. So solid state limit switches don't have to be powered, right? You understand that? Because they're mechanical, right? You don't understand that. That would be like the light switch in your house. The switch itself is not powered. You're the source that moves it, right? You understand that? It controls power, but the switch itself is not powered. Now, if you've got a light dimmer in your house, that is an electronic circuit. So you got, not only does it power up, but it's also got to have power to be able to control the dimming circuit, right? You understand? So it uses power. Consumes power. Are we okay so far? Solid state limit switches. Contact closed with, what the first one we'll look at is, and this falls into the category of magnetic reed.